We'll get started in just a minute here. Give it a chance for people to join. See some names we know. Okay. All right. Well, hello, everyone. I'm Renee Yager. I'm the Director of Marketing at EPC, and welcome to today's webinar, Design with GaN for More Efficient and Reliable Solar Inverters and Energy Storage Systems. Before we get started, I would just like to go over a few housekeeping items. You all have the opportunity to submit text questions to the panel by typing them into the Q&A feature at the bottom of your screen. You may send in your questions at any time. We'll collect all of these and address them during the Q&A session at the end of today's presentation. So now I would like to introduce our speaker today. Andrea Gorgerino is the Director of Global Field Application Engineering at EPC. Andrea is an engineering leader with several years of professional experience in leading design and development of power electronics products, including hardware and firmware. Andrea, I'd like to thank you so much for joining us today.
Thanks, Renee. And hello, everybody. So let's dive right in on this webinar. Let me start with the agenda. So I'm going to cover today some market trends for solar and how EPC plays into that. We'll talk a little bit about the solutions that are out there, and then about how GaN benefits these applications. I'll go over some specific GaN products that can be used in solar, and finally, a few customer examples where our customers are using GaN in solar application, and they allowed us to share with our broader audience these examples. So let's dive right in. So first, the market trends, to give you a little bit of background on EPC. EPC is a leader in GaN semiconductors. We have a market share of over 80% in our market, which is basically under 400 volt devices for IC and discretes. And you can see here the two charts on the left-hand side is the discrete current ratings versus voltage classes, and on the right-hand side is the same for IC. The green dots are EPC. And we really dominate the below 400 volt areas. We have more than 80 devices available for off-the-shelf delivery. Several of them are automotive qualified since 2014. And this also explains a little bit the background of what I'm going to talk today. Of course, is the areas in solar, which is a huge market area where EPC GaN FETs can add value. So let's talk high level about the topologies. First, on the inverter itself. There are three main ones. String inverter is the most common one. Basically, you take all the solar panels, you put them in series. This generates a high voltage DC bus, which goes to the string inverter and converts it to the AC grid. This is the most common topology. It's very scalable and is used from residential all the way up to utility scale systems. The second approach is the microinverter. This one basically puts a single inverter for each panel. So you have the low voltage DC coming into the microinverter, going out as an AC, and all the AC is then put in parallel. This is more common in a smaller system like residential and commercial systems. And AC here typically is around 220 volts RMS, and that's why it's more used in the smaller systems. The last option is an optimizer plus string inverter. So it kind of combines a little bit of both. Each panel is connected to an MPP Optimizer, which still is a DC systems. They're all put in series and they all tie into a string inverter, similar to the first case. So let's look a little bit about how these work in more detail. The first one is the string inverter here. So each string typically is at least 2 kilowatt and can be much, much higher. As I said, these are also used all the way to utility scale systems. It has the lowest initial equipment cost per peak watt because you have a single inverter systems. Some limitation is it might require some additional module level power electronics when you are required to comply with these new required regulations on module level rapid shutdown. These are becoming more common in the Americas, in Europe, and so you'll need additional electronics for that. Usually, The lifetime for these string inverters is a little bit lower than other systems. It's 5 to 12 years, which means it will need to be replaced most likely during the lifetime of the solar system, which is more like 25 years. Another characteristic is the maximum power point tracking is done at the string level. And that could be critical, especially in cases of shading or partial shading. It also means that if one single panel malfunctions, it will affect the output power of the whole string. The next option is the microinverter. The microinverter, as I said, connected one inverter to each panel. So the typical power level is about 350 watt for one panel, or 500 watt, or up to 6 panels, and you were getting into 2 kilowatt range there. It has the advantage of being fully scalable. You can add more panels very easily, and monitoring capability are very good since each panel can be monitored individually. It also complies directly with the module level rapid shutdown regulations since you have the electronics right there. The panel failure, one single panel failure does not affect the whole system. They're all independent. And also the MPPT function is done on the individual panel, which offers the best performance. So these systems typically offer longer lifetime, 20 to 25 years, to match the overall lifespan of the solar system. So they don't need to be replaced during the lifetime. The final one was the optimizer plus string inverters, kind of a combination of the two. Typically, you find single or dual panel solutions, which means in the 400 to 800 watt range. It has similar advantage to the microinverter we just saw, like the optimum MPPT done at the panel level, of course, as well as the monitoring. But it has lower initial equipment cost. This is simply a DC-DC converter. It's a simpler, cheaper power electronic system. It is less scalable than the microinverter system, as the size of an inverter is fixed, and so you can't just add more panels. It has a similar lifetime requirement to the microinverter. We're talking about 20, 25 years. So again, it doesn't need to be replaced during the lifetime of the system. The second series of topology we should talk about is the energy storage system, which are becoming more and more popular. So these are some examples for residential commercial battery energy storage systems, the ones that are commonly known as behind the meter. And there are two options here. One is the DC coupled, and the second one is the EC coupled. As the name implies, in the DC coupled, you tie together the DC buses from the solar panels and from the battery, while in the AC coupled system, you tie them after inverters, which means you do an AC coupling of the two, the panels and the batteries. So what does that mean? For a DC coupled system, the advantage is it has a lower initial equipment cost. You only have this one bidirectional DC-DC converter, so less additional things to add, which also means higher efficiency since you have fewer conversion stages. The DC-DC converter is a bidirectional capable DC-DC converter, of course. What it allows you to do is basically to handle the battery state of charge with more degrees of freedom, which also means you can use lower voltage battery packs. And this can be useful, for example, to reduce the cost of the battery pack system. The AC coupled, instead, as I mentioned, has more electronics. Basically, you have an additional inverter for the battery and you couple the AC together. This means higher initial equipment cost. You have more power electronic blocks in here. It also means lower efficiency. The energy needs to go through more of these power conversion stages. It does have higher flexibility. It is easier to retrofit systems. You can just add more batteries or add batteries to an existing system since it is AC coupled. You can have also here an optional bidirectional capable DC-DC converter. This again is an optional block. And if you systems that decide to use this, do it for the same reason as I mentioned before. Basically, you have more degrees of freedom in handling the state of charge of the battery, which means you can also use different voltage levels, usually lower voltage battery packs, to optimize the system. So let's talk now about the GaN benefits and what they can bring to solar systems that we just saw. High level, the first thing that GaN brings to the power electronics is higher efficiency. And higher efficiency solar systems means higher energy production, which is, at the end, what we care about. It also brings higher switching frequency capability. Typically, silicon FET systems are running at 100 kilohertz maybe, and we can definitely go to 800 kilohertz, maybe even higher. And this is for power density. This can be used in several ways. It can lead to small and thin designs, or it can lead to higher power in the same form factor, for example. GaN also brings excellent thermals, and this is really useful to avoid complex cooling to simplify the system itself. And we also bring excellent reliability. As I mentioned, 25 years is a typical requirement for solar systems. So we'll dive into all of these in a little more detail. First of all, let's just look at parametrics for GaN FETs. These are 100-volt GaN FETs versus silicon MOSFET. I'm comparing here against two Infineon Optimus 5 and Optimus 6. These are really the best in class of 100-volt silicon FETs. These are both in a 5x6 package, 30 square millimeters, and we're comparing to EPC 2071, which is chip scale package GaN FET, and EPC 2302, which is QFN GaN FET. Both GaN FET are less than half the size of the silicon FETs. However, they have lower RDS(on), as you can see from the table, and also all the charge values are lower, and these translate in the capability to switch faster, basically. The other area I want to highlight here is the QRR. So silicon MOSFET have this body diode, which has reverse recovery. And this can be a significant contributor to losses for hard switching applications. GaN FETs rely on a different mechanism for conduction in the reverse direction. They don't have a diode, they don't have reverse recovery. This is really important. I'll show you in the next slide how relevant it is. The last comparison here is on the thermals. There's two main paths that we consider when we look at thermals for silicon and GaN FETs. One is to the bottom of the package towards the PCB. One is to the top of the package where, for example, a heatsink can be mounted. And especially to the top, you can see that the GaN FETs have really much lower values. And this allows for very high power density designs. We'll go a little bit more in detail on how to do that. So first, let's look at an example in an application of how these parameters translate in actual losses. So this is a comparison with, this is a formula-based calculation, typical formula-based calculation. This is actually the formulas from the GaN book, the 3rd edition, but similar to other formulas that our manufacturers use, using same assumptions for both. I'm comparing here the Optimus 6 device against the QFN EPC 2302. The silicon device is operating at 150 kilohertz. The GaN FET is operating at double the switching frequency, 300 kilohertz. The other conditions are the same. And you can see the losses are basically about almost half of the losses of the silicon. And if you look at the comparison of the breakdown of the various contributions, of course, the RDS(on) lower, so lower conduction losses. And again, this is half the physical size of the device. Switching losses are also very similar with double the switching frequency in terms of overlap losses. A very big contributor here is the dark blue bar you can see here on the left. That's actually the reverse recovery. As I mentioned before, reverse recovery in hard switching applications can be very significant. It's also very hard to estimate. This is a rough calculation. It's based simply on the QRR from the datasheet of the silicon FET, which is given at a fairly low DIDT. So again, difficult to estimate, but I think it gives a good idea of how important that parameter is when you actually have to make a real applications. Maybe the other quick comment I want to make here is the orange one. That's the PSD. That's the dead time diode conduction losses. As I mentioned before, GaN FETs have a different mechanism for reverse conduction. That's not a diode. And one of the characteristics is that it has a higher drop. So typically it leads to higher losses. But you can see here in the calculation, it's actually lower. And the reason for that is that GaN FETs switching faster, again, this is done with the same gate driver, same assumptions. You can use lower dead time. The assumption for dead time here was done in the similar way for both devices. Basically, it's 2 times the sum of all the transition times to give some margin. And again, since the GaN FETs are switching faster, the dead time tends to be much smaller. And this means you spend less time in that condition, which means lower losses overall. So the next thing we want to look at is the thermals. I already mentioned there are 2 main paths we need to look at when we talk about thermals. The first one is from the junction to the board. And that's what we see here on the left-hand side chart. This is RTH junction to board versus device area. It has blue and red dots for silicon and GaN. Basically, they all sit on the same curve. It's proportional to the area. So similar behavior here when you talked about junction to board. GaN is smaller, as I mentioned before. So for the same RDS on, you tend to get slightly higher thermal resistance to the board. However, we look at the right-hand side chart. This is the junction to what we call case, which is basically the top of the device. And here, for the same area, the GaN device really shows a much lower thermal resistance. And that's because with our packages, you have almost direct access to where the heat is being dissipated. And this really allows designers to extract heat from these very small devices very effectively, which leads to these very high power density designs. So let's talk a little bit about these 2 paths. So the first one is towards the PCB. Of course, here we want to use basically the PCB copper for heat spreading. And we do that basically with vias. So on the left-hand side, you have a design without any vias. And so what we want to do is we want to add vias. We can do that by adding vias around the device themselves, right? As you can see in the middle picture. Or we can add vias under the bumps themselves, as you can see on the right-hand side. This is on the right-hand side. This is typically what we do on all of our reference designs. It provides really the best performance to utilize the PCB to dissipate heat. But the second way to extract heat from our devices is from the top of the device. As I shown in the table, we have very low thermal resistant junction to the top. And to take advantage of this, we have this very simple and easy and low cost method of doing that. We're using these little standoffs, which are mounted during the reflow of all the other components of the board. They set, in this case, typically we use 1 millimeter height from the board, and you can mount a heatsink to these standoffs directly with some screws. We use a TIM, of course, between the heatsink and the components, which gets compressed during assembly. There are some very good TIMs available right now, up to 17 watts per meter Kelvin. These are really lead to some very efficient cooling of the devices. And again, the devices are very small, so the TIM amount required is very, very small. So let me show you just an example of calculation of how this looks like. So what I did here, I used our GaN FET thermal calculator. It's an online tool that you can find on our website. I put the link there. And it's a very nice little tool. You can basically change many parameters like, of course, which device, how much heat. You can change how close half-bridge devices can be to each other. In this case here is a single device. You can change the PCB layers, the amount of copper, the number of vias. You can put a heat sink, the airflow. There's actually a heat sink calculator in there also. So a lot of options. I just took a couple of examples here, put a few numbers to give you a feeling of the impact of the various things I just discussed. So as a baseline, I've used the vias under pads. This is what we use on all of our reference designs. And you can see here, if you move those vias, for example, let's move up, if you move the via from under the pad to outside of the package, you lose about 7%. If you remove the vias, you lose about 25% of RTH, or you increase the RTH by 25%. Now, if you add a heatsink on top, this is a fairly small heatsink, you can reduce by 5 the thermal resistance. And this is how you get really the high power density designs. So an example, you can go online and put on your own parameters and really play around with the effects of all these different thermal paths. Very good. So the last topic I want to talk about is the proven reliability. So as I mentioned, lifetime is very important for solar application. 25 years is a common target. EPC has been doing reliability testing for a very long time. We have an approach that we call test to failure. And the idea is basically to test all devices way beyond the standard JEDEC requirements for that typical silicon manufacturers utilize. And this basically test to failure has allowed us to identify the intrinsic failure mechanism that GaN devices have, which are a little bit different than silicon. Once these failure mechanisms have been identified, we then develop a series of physics-based models. And these allow us to predict the safe operating life of a product over a more generic set of operating conditions. So different operating conditions that where the tests were actually done. All of this is documented in a lot of detail in our reliability report. We are on the phase 14. I mean, that's the 14th year we make it. The phase 15 should be out actually any day. These are available on our website. Again, quite long. It has all the details of the test to fail, the failure mechanism, the physics-based model, and how to utilize them. Here today, I'm going to talk about mainly three things in high-level approach, of course. More details can be found here. And the three main failure mechanisms that we want to discuss for these applications are basically the gate bias, the drain bias, and the temperature cycle. So let's dig in a little bit. So the lifetime for the gate bias. So lifetime for the gate bias is basically based on HTGB. This is a high temperature gate bias test. We're showing the curves of time to failure versus gate bias voltage here on the right-hand side. EPC GaN FETs are rated at 6 volt, maximum rating on the datasheet. So you can see that dashed vertical line, it's at 6 volts. And basically the failure, the PPM rate calculated for 25 years is below 1 ppm at 6 volts. By the way, in normal operating conditions, we are between 5 and 5.2 volts, which is even a lower ppm rate. So very, very low ppm rate for gate bias. This is also reflected in our field return rates, which are basically almost, I would say, no gate failures really in the history of EPC. We have an extremely reliable gate, and we have all the data to show that. The next failure mechanism we want to talk about is the lifetime for drain bias. So this is where an area where this is very different than silicon FETs. So the main failure mechanisms when we talk about drain bias for GaN is dynamic RDS-on. I'm sure a lot of you have heard about this word. Dynamic RDS-on is the phenomenon where during normal operation, because of drain bias, the RDS-on of the device actually increases. In the early days of GaN, like 20 years ago, they would basically increase the RDS-on while they were operating on your bench, and within 10 or 15 minutes, they would get so hot they would blow up. So we've come a very long way since those times. Basically, dynamic RDS-on is not an issue anymore for our latest generation devices at EPC. You can see here a chart on the right-hand side. It has time versus normalized RDS-on. That's basically one is where it starts off, and the percentage shows the increase. The right-hand side of the chart is basically 25 years. You can see it's less than 10%. 10% is what we use as a criteria for dynamic RDS-on. So the device here was operated under continuous hard switching at 100 kilohertz, and 80% of the maximum rated voltage. So for a 100 volt device, that's 80 volts, and at 80 degrees C, which is the typical mission profile. One comment is the acceleration factor versus switching frequency is quite low. That's why we show 100 kilohertz. You can find all those curves for different frequencies in the reliability report I mentioned before. And again, as I mentioned, the increase after 25 years will be about 10%, which is within our spec for dynamic RDS-on. I also want to stress this is not a hard failure. So after 25 years, you're increasing RDS-on by 10%. There's no failure here. And especially if you remember the chart of losses I've shown, the conduction losses are actually fairly small percentage of losses, at least in the hard switching application. So, this is really not a concern under any operating conditions that we want to consider. So the last lifetime failure mechanism we want to look at is the temperature cycling. So the temperature cycling, this is where it's more similar, I would say, to silicon devices. At the end, it's a thermomechanical type of failure. Our standard testing is doing temp cycling between -40 is 125 degrees C. That's a delta T of 165. And from the right, the chart that you see here on the right-hand side, we can achieve 1,200 cycles with 1% failure rate with underfield material in these conditions. So this chart was generated with EPC 2206. This is a worst case scenario. This is the largest device that we make. It is larger than the usual devices that are used in solar, like 2218 and 2071. But again, it's a worst case. We're working on generating similar data on these smaller devices and should be available soon. So as I mentioned, we do recommend Underfield. These are the two that we tested that provide good performance. They're shown in the chart. You have to pay attention how to pick the Underfield. There's quite a few interesting observations and test results in the reliability report. I suggest you take a look at that. But basically, with these assumptions, our typical solar mission profile requires a delta T of 60 degrees C. And with that acceleration factor, that means we can survive 15,000 cycles, which is equivalent to 41 years with a 1% failure rate, which is much higher than the 25 years requirement. So again, based on these three main failure mechanism, we feel confident that GaN can achieve the 25-year lifetime required by solar applications. So very quick, let's take a look at some of the devices that can be used in solar systems. So first at the MPP Optimizer, which is typically a hard switch buck boost topology as shown here. So the devices that are used, since these are MPPTs are connected directly to the solar panel, they're typically 100-volt rated devices. So 2218, 2204 are the most common one, as well as the QFN GaN FETs that we offer now, like 2302 and 2306. Now, if you start putting more panel in series, then you might need higher voltage classes devices. And so we're offering here, for example, EPC 2059, which is a 170 volt device in a chip scale package, and 2215, which is a 200 volt. But we also have QFN GaN FETs like the 2304 in a 200 volt. The next one is for the microinverters. Microinverters, I'm going to show two different ways to do it. The first one is a flyback, very common. Typically, I'm showing here a two-phase flyback, for example. Because of the reflected voltage from the transformer, these require typically higher voltage class devices. So EPC 2059 is a chip scale package, 170 volt chip scale package. And we also have QFNs in the 150 volt class, like the 2305 and 2308, which are well suited for this application. Another topology for microinverter is the full bridge topology. In different versions of resonance also used typically. So this topology allows better efficiency and better power density than the previous one. It's becoming more and more common, I would say, in new designs. Because it's a full bridge, the voltage requirement is lower than the previous. So typically 100 volt devices is what is used. So again, the 2218 is the chip scale package version, and 2302 and 2306 are the QFN GaN FETs that we offer for this socket. Finally, for the battery energy storage system, so we're talking here about the bidirectional DC-DC converter, which is mainly used in the DC coupled, but some AC coupled systems also. So what we'd like to propose here is a 3-level solution versus the standard 2-level solution. What this allows is basically to use 200 volt FETs instead of 600 volt FETs for the 2-level. And this means lower losses because the 200 volt devices are that much better. But it also means that the inductance is actually 4 times smaller, and the overall system magnetics and power density can be higher, therefore. We're showing here on the right-hand side our demonstrator. This is a 3 kilowatt 2-phase system, so 1.5 kilowatt per phase. It is using a 200 volt EPC 2218, operating at 150 kilohertz. And this allows us to achieve a maximum 98% peak efficiency in a battery charging mode. So again, 200 volt devices is what would typically be used here, like the 2218, which is a chip scale package. And we also have QFN GaN FETs in 200 volt class, in the 200 volt class, which are the 2304 and 2307. Finally, I'd like to share 2 customer examples that these customers have allowed us to share with a broader audience. I think they're very interesting example how to use GaN in solar applications. So the first one is a solar optimizer by BRC. So BRC had a previous design. It was called the M412, which was basically a 12 amp optimizer rated at 400 watts. So they moved from silicon FETs to GaN FETs, and they were able to achieve 14 amps and 500 watts in the same board size. But they also were able to increase the switching frequency about double. They went to 350 kilohertz in this case. And this allowed to reduce all the passive components inside the box, like capacitors and inductors, for lower overall system cost. And this is this optimizer is using the EPC 2218, which was one of the devices shown in the previous tables. The next example I have is the microinverter. This is a solar native JT350. It is rated as 350 watt. In this case here, solar native utilized the 2218 and 2204 in the boost stage for the MPP stage of the microinverter, switching at 1 megahertz. Overall, they were able to achieve 5 times the power density of the silicon MOSFET design. That would be the Enphase IQ7A, with the same European efficiency. European is basically the averaging method for measuring efficiency. So one of the reasons they went this way is they were able to make such a small frame for the inverter. You can see here is basically 350 by 25 by 22 millimeters, so kind of long, but very small. And the idea was to be able to integrate it into the module frame. So another interesting example where GaN can add value in solar systems. So just in summary, I think in solar application require basically high efficiency, high power density, and high reliability. And I hope I've showed you today how GaN devices can significantly improve all of these parameters when compared to silicon MOSFETs. And all of this also at a very attractive price. So I encourage you to take a look at our products and feel free to ask any questions. Thank you very much for your attention.
Okay, thank you, Andrea. So now we're going to start answering the questions that were submitted during the presentation. Just as a reminder, you can still submit your questions by typing them into the Q&A feature at the bottom of the screen. And so our first question today was, can you offer an ideal diode, meaning integrated GaN FET with built-in controller?
Sorry, say it again.
Can you offer an ideal diode, meaning integrated GaN FET with built-in controller?
For the type synchronous rectification products. We don't have that product today. We're definitely looking into it. There are also a few IC partners which are integrating their controllers with a GaN FET to basically create a synchronous rectification FET, which would be an ideal diode. So that's the idea. So I don't think any of these products are released yet. Keep an eye out for them. They should be coming out. But you can also, if you look on our website, we also have several IC recommendations for synchronous rectification that are meant to be utilized with GaN FETs. So you can build it yourself by using one of these ICs and one of these GaN FETs. I hope this answers the question.
Okay. Next question is, what kind of process are you using on your GaN ICs? Is it CMOS or bi-CMOS for logic and GaN for power MOSFET? Single die
No,
or
these
hybrid?
are actually all GaN. Actually, there's a little picture here. You can see it here. This is one of our first ones that we did. And these are the FETs, and this area right here, that's basically the GaN IC. So it's monolithic. It's all made in GaN. So it's GaN IC technology. There are some limitation, of course, in GaN IC. We can't do all the things you can do in silicon, but you can do a lot of them. And having the driver right next to the FETs has a lot of advantages for performance because you eliminate all those parasitics, and you can drive these things really, really fast.
Okay. What is the accuracy of the LT Spice, eSpice, eGaN FET model compared to real eGaN FET? Could you roughly estimate the accuracy in percentage, and is there a model limitation?
Well, I think percent is going to be difficult. I would say it's very good. Also, it depends what are you comparing. So, for example, if you're comparing the datasheet curves, pretty much they match very well, right? So maybe within a few percentage points. When you start talking about dynamic behavior, of course, it's trickier, but it's also very hard to compare because when you really want to see losses, for example, out of a SPICE model, you shouldn't model just the device. You need to model everything, and that's probably one area where it gets very tricky to understand where the errors are generated. So you need the parasitics of the board, you need the gate driver model, and it definitely gets harder. So the simulation I showed before, they were not SPICE based, they were formula based. They're easier to understand because you can break down the various types of losses and understand what the contributions are. I feel SPICE models can be more accurate than that. And if you look our textbooks, especially the third edition, fourth edition, they have actually some. We tried to do this in the past to compare simulation versus actual measurement. As I said, it comes down to how accurately you model the whole system versus just the device itself. But for datasheet curves, very accurate. For losses, again, I think there's many other considerations to take into consideration.
So there's a question on vias from slide 19.
Yes.
It says, is the number of vias 21.9 or 2.19?
I'm sorry.
Oh, and your first
this one
line there. Oh no, back where you are, the table. So it says number of vias. The first line says 2.19 degrees C per watt.
Yeah, this is the result of the thermal pool calculation.
Okay. The question was, is that a typo?
Oh,
it's supposed to be 21.
It's a typo. I'm sorry. Yes, it's a typo. I'm sure it's 12. Thank you for catching that. I'll correct it before we send it out. Sorry. Okay. The 24% is correct though.
Okay.
I have it in the Excel table. Yeah, I must have missed the digit there in the copy and paste.
All right. What
so it's probably 22. Sorry, it's probably 22.9 or 21 point. Yeah, the digit is probably
the
wrong.
digit's off, right?
Yeah, I'll go check it in the original data. Thank you.
Okay. What is the surface material of your yellow eGaN FET package like 2218, 2059? Is it SiO2? They're all the same, right? The surface?
Yeah, the yellow. So you're right. It's basically the passivation scheme. I am sorry, I don't know exactly. It probably is, but I wouldn't know exactly what it is. So yeah, I could probably double check that. Yeah.
Okay. What kind of metal are you using on top of the EBC 2305, the QFN? Is it solderable?
Yes.
Okay. Can you show or give a link where the application of underfill is shown?
Yeah, so I think the most information on underfield is shown in the reliability report. There's a whole section on temperature cycling, underfills. We've tested several different kinds. Some actually make the performance better, like the ones I showed in the chart. Some make it worse. And we have some guidelines on how to pick the right one, right? It has to match the CTE mainly of the board and the device. That's typically the criteria.
Okay. What is your solution for huge EMI?
for huge EMI is like, don't have huge EMI. I think that's the solution. So EMI is a difficult topic. It is very much related to how not just how fast the device is switching, but all the parasitics that are linked to that switching. So ringing, for example, and reverse recovery is another big contributor to EMI. So of course, there is a component of I would say the spectrum being generated during switching events, which naturally is proportional to the DVDT and the DIDT. But more so, these other elements are big contributors. So we have found that with proper design techniques, which means proper layout techniques mainly, we can have extremely clean waveforms. This is one of the advantages of GaN FETs. They're very linear. They have extremely low parasitics, especially, all of our packages, very, very low common source inductance, which really allows us to have very clean waveforms during switching events, which reduces the ringing. And our customers have found that they were able to address the typical EMI requirements with just very similar methods as the ones used to get silicon designs to pass. I would say, again, in some cases, there can be some advantages of using GaN FETs, like the fact that there is no reverse recovery, because that is, for example, a very large contributor to EMI noise that is not present here.
Are your GaN FETs manufactured in modules too, in addition to discrete transistors?
No. I mean, depends what you mean by modules. So we don't. We sell the products that I've shown. We do have partners that take these products and put them in different types of products. And for example, some of them are DC-DC converter modules that are available on the market using GaN. And several manufacturers are doing that, like TI, MPS, and others in the market.
Are you using a P-channel GaN in your own IC?
No, that we wish we would.
Is the reverse conduction loss of GaN FETs worse than that of silicon FETs body diode when the gate is off?
So I tried to show a little bit of that here. So as I mentioned, GaN FETs don't have a body diode, so they basically rely on the self-turn-on mechanism. So what it means is, if you're conducting current in the reverse direction when the gate is off, that typically happens during the dead time, you get a voltage drop that is higher than a silicon FET, which basically in that same time would basically have a diode voltage drop. So the voltage drop is higher, which means higher power loss. But the power loss is instantaneous power loss. The average power loss also means how long you're spending in that condition here and there. So what I did in this calculation here is I've used different dead time for silicon and GaN. The way I calculated the dead time, I just used the same criteria for both. I took basically the sum of all of the transition time and I multiplied it by 2. I don't remember the exact number. It came out to something like probably around 12, 15 nanoseconds that time for the GaN, and maybe something like 60, 70 nanoseconds for the silicon FET. And when you use that criteria to define the dead time, which I think is a very reasonable criteria, 12 nanoseconds is a very common number that we use in our reference designs, for example, even less sometimes. Then you get these numbers here, and you can see the PSD, that's the contributor here, is actually lower for GaN FET. That's because the conduction time is so much smaller. So yes and no, basically. But in real application, what matters is the average power loss, not the instantaneous power loss. So the instantaneous power loss is higher, but the average power loss can be lower if designed appropriately.
Are your devices protected from thermal runaway?
Well, not sure what that means. Now, like these are devices, so there's no active feedback mechanism. This is just a discrete device. I'm wondering if the question means something more like if you look, some of the thermal runaway mechanism are linked, for example, to RDS on, right? So in a silicon fed, the RDS on increases with temperature. So basically when the RDS on gets higher with temperature, and that's same mechanism with GaN FETs. I'm not sure about the question actually. So as I can say, all I can say is similar behavior for RDS on as a silicon FET. It depends on the part. The temperature coefficient is slightly different for RDS on, but usually slightly lower, but very similar. The threshold also has a temperature coefficient. Silicon FETs have a quite negative temperature coefficient, which means it gets lower with higher temperature. GaN FETs have much more stable threshold, so it's almost constant over temperature, which is a better behavior, I would say. But that's all I can say. I'm not sure I fully understand the question.
Does your process allow for the creation of GaN fast SPDT analog switch or multi-switch?
So let's take one at a time. So multi-switch, yes, we can put more switches on the same chip. We do so several versions of it. GaN fast, I'm not sure. Is that the Navitas system basically, or can you repeat the question maybe?
This is a GaN fast SPDT analog switch. I think.
Not sure what that is.
Okay. All right. 1 second. Oh, could you offer switching and power GaN diodes in the future?
No, I don't think we have a plan to offer diodes.
Okay. Okay, so there are no open questions right now. If there are no more questions, we will wrap up. I'll just say thank you, Andrea. Thank you, everyone, for attending the webinar today. If you do have additional questions, please send them into info@epc-co.com. Everyone will get a follow-up email within 24 to 48 hours, which will have a link to view a recording of today's webinar and also a link to the slide deck. And lastly, be sure to register for the webinars in the upcoming series, GaN for Consumer Applications, which kicks off February 15th with Design with GaN for High Fidelity Class D audio for a better listening experience. You can visit our website at epc-co.com for more information and to register. Thank you for joining us today and have a great rest of your day. Thank you. Thanks again, Andrea.
Thank you.